So, in psychology, what we're trying to learn about are called population parameters. And a population parameter is really just simply a summary value. It's like a statistic, but it's for a population. So in other words, we just want to learn about humans. That's kind of the whole point. Now, the way we do this is by, collecting our data and doing our sample statistics and computing all that kind of stuff. But then we have to just kind of make an assumption that those sample statistics are similar to what we would find in the population. We can never be 100% certain that our sample is going to be just like the population it comes from, but we have to kind of make that assumption. Now, the reason why we can never be 100% certain is because of something called sampling error. And sampling error just refers to the fact that that sample is just going to have some kind of random variability. There's always going to be some random variability in any statistic from sample to sample. Samples are different, everybody's different. Those individual differences are going to be driving this variability. So that can be problematic. And the fact that no sample is going to perfectly represent the population it comes from will always introduce some doubt into your experiment or your non-experimental study that you're doing. Those statistical relationships you might observe could be the real thing. They could be evidence that there's something interesting going on here, like there's some effectiveness for a treatment you've developed or something like that. That's one possible interpretation. That there is a real relationship in the greater population, and this relationship you found in the sample is evidence for that. So that's one possible implication. The other implication is that while you did find something, while you found a relationship in your sample, it's not real. It's just due to error. It's due to random variability, and there is no actual relationship in the population. So, to put it more simply, when you find something in your sample, it could be just for that sample, or maybe it represents something greater. Those are the two possibilities. And the way we determine which of these two possibilities is correct is by doing hypothesis testing. So this brings us to what's called the null hypothesis. The null hypothesis, which is often written as H sub 0, as you see right here, this refers to the idea that there's no relationship in the population, and any relationship that you might see is just due to sampling error. So this is that implication number 2 I was describing earlier. To put it more simply, the null hypothesis is the prediction that there is no relationship, that something does not exist. So whenever you read a null hypothesis, what it's basically saying is there is no relationship between this and that, there is no significant difference between these groups, there's nothing. The null hypothesis is a prediction of nothing, basically. And it might seem strange to make such a prediction, but we have a good reason in science to use null hypotheses. And it all comes back to something called the burden of proof. Now, this is kind of a little bit of a divergence into philosophy, but philosophy is the fundament. It's the basis for all science. So it's really important for me to try to explain this as best as I can. So the whole idea behind the burden of proof is you can't prove that something does not exist. Okay? Because if you go out there and you try to prove something doesn't exist, and you look for it and you look for it and you can't find it, that doesn't mean that you have conclusively proven it doesn't exist. Maybe you just failed to find it. Failure to find evidence of the existence of something could simply be due to your method. Maybe you did it wrong. A famous quote about this is, "The absence of evidence is not the evidence of absence." It's a little confusing, but if you think about it, that makes a lot of sense. You know, if you go out there and you look for something and you fail to find it, that doesn't really prove anything. That's the whole idea here. So, we can't prove something doesn't exist. But we can prove it does exist. And that's why we have the null hypothesis. So with the null hypothesis, we just make this assumption that there's nothing out there, and then we try to prove it wrong. We try to find evidence to reject that assumption. We can't prove that assumption, so we just kind of have to prove the opposite. So what I mean to say is, as scientists, we go out there to try to, first of all, set up these assumptions that something's not there, and then prove it wrong. That's the whole idea. But this is still kind of confusing, I'm sure. This burden of proof philosophy, if you really think about it and you think about it, it does make some sense, but it is a little bit confusing at first. So here's a classic example. It's called the celestial teapot. Let's say that there's this teapot orbiting the sun. Somewhere in our solar system, there's a teapot in orbit around our sun. And you go out there and you look for it and you look for it, but you can't find it. Well, as I was saying, maybe you just didn't look in the right places. Maybe you didn't look in the right times. There's tons of possible orbits around our sun. Maybe you just failed to find it. In order to conclusively prove that there's no teapot orbiting our sun, you would have to check every possible orbit to be certain that it doesn't exist. And I'm no astronomer, but that seems like an impossible task. At very least, it seems incredibly inefficient and time-consuming. It would make a whole lot more sense for the person saying that there's a teapot out there to simply show you where it is. There's billions of possibilities of places it could potentially not be, but if it actually exists, there's only one place that it actually is at. So you can see the difference between those two things. Like, it's very hard, if not impossible, to prove something doesn't exist. But it's relatively very easy to prove that it does. You just have to find one instance of it. You need to go out there and you need to find it just one time and you're done to prove that it does exist. So this is the whole idea behind the burden of proof. It's much easier to show that something is real than to show that something is not real. And that's why we assume the negative and try to prove the positive. So that's the whole logic of null hypothesis testing, but here it is in a bit of a different way. First of all, step one, we set up this null hypothesis and we assume that it's true. In other words, we make this assumption that there's no relationship between the variables we're interested in that population. Step two, we want to determine how likely this relationship we observed in our sample would be if the null was true. So what's the probability that our observed relationship, you know, this potential relationship we found in our or in our sample, how likely is that simply due to sampling error? And then step three, if we determine that sampling error by itself is not sufficient to reject this observed relationship we found, then we get rid of the null. We would reject the null hypothesis. However, if sampling error does seem like a good explanation, then we would retain the null. We would keep that null. And that's the whole idea of hypothesis testing. But there's something I mentioned in there that is a little bit confusing. I should maybe explain that a little bit better. When it comes to deciding how likely sampling error, you know, is a problem in your hypothesis test, it's kind of hard to quantify that unless you use some statistical procedures we've developed. And every statistical procedure you could use for a hypothesis test will give you various kinds of information. And one of the most common kinds of information that we use, one of the most classic pieces of information that we use to decide whether we should retain or reject the null is called a p-value. So to put it more simply, a p-value is the likelihood of getting the observed sample if the null hypothesis is true. So you want a low p-value. The lower your p-value, the better. And we do have this kind of arbitrary, cutoff point of 0.05. Pretty much any science you read, any science you get into, you're going to find that p-value of less than 0.05, generally that means that you're going to reject the null. So a lower p-value means that there is less likely it's simply due to sampling error. But p-value is, like I said, it's just an arbitrary thing. The lower the p-value, the better. So if you have a p-value of 0.05, that's good. If you have a p-value of 0.0005, that's better. But it's just an arbitrary thing, and it's based on what we call the alpha level. Or you could also refer to this as your level of significance. This is just what you decide to be the maximum allowable probability that your research result is obtained by chance or sampling error. So p-value and alpha level, it's basically the same thing. So if you set your p-value higher, then that just means if you set your alpha level higher, then that's going to bring up your the p-value that's required to find a significant result. If you set your p-value lower, then that's going to move down that p-value as well. You can basically think of alpha level and p-value as the same thing. So if we set our alpha level to 0.05, then that means we'd want to find a p-value less than 0.05 to find something that we would consider statistically significant. And when we say something is statistically significant, we just mean these results seem to be legitimate. It's not due to sampling error. But in general, people misunderstand what a p-value is. People often misunderstand p-value in thinking that can be defined as the probability that the null hypothesis is true, that this sample result occurred by chance. And this is where it gets a little bit confusing. All I'm trying to say is that the p-value, that doesn't directly translate to the probability it was sampling error. That's generally how we think about it, that's generally how we talk about it, but it's not that simple. Nothing is ever as simple as it should be, it seems. So the p-value is not the probability that any particular hypothesis is true or false. P-value is just this kind of arbitrary cutoff point where we decide whether or not we should reject the null or retain the null. That's all it is. And in general, when it comes to these p-values and alpha levels, these are things that we see pretty dramatically. Like the p-value you can expect to see varies dramatically depending on a couple of things. The two big factors are sample size and the strength of that relationship. So there's like a trade-off here. For a larger sample, you're going to see it much more likely that you'll get a lower p-value. For a smaller sample, it's going to be a lot harder to get a low p-value. So a joke that we often make in science is, if you want to find a statistically significant result, just get a bigger sample, because larger samples are more likely to produce significant results. But p-value definitely isn't the end of the discussion. If you find a statistically significant p-value, that's great. You've collected the statistics required to reject that null hypothesis. But that's not the end. That's just the beginning. The next step is to see if your result is practical, if it has practical significance. Just because a relationship is statistically significant, that doesn't mean it matters. That doesn't mean it's important. That doesn't mean it's practical. And in fact, you could find a very, very low p-value showing a very clear statistically significant result that doesn't matter at all because it's such a minor result. The relationship could be so weak it's barely noticeable. So after we determine statistical significance, the next step is to try to measure what's called the practical significance. In other words, how important is this result? How useful is this result in like a real world context?